flew to the Bahamas just for this lesson? Because today we're learning about water. JK! Water. You may think it looks like this, but what if I told you this is only one of water's three phases? It's really more helpful to think of water as looking like this. When, when I think of water, I think of it only in its liquid state, right? The thing that I drink, a cup of water. But when it's frozen, when it gets colder and turns into a solid, it's called ice. And then when it's heated, it's called a gas, and you might think of it a few different ways. It could be called water vapor or maybe cloud, right? What if I told you that water actually looked like this? What? Mickey Mouse? My father is one of the smartest scientists I've ever known, and he always described the water molecule as the Mickey Mouse molecule. I'm going to show you what it looks like when you zoom in way to the molecular level of water. It looks like Mickey Mouse. You ready? Here we go. Water, when I zoom way into its smallest parts, is broken down into two different kinds of things. These little gray circles, those are hydrogen. Remember we talked about salt, sodium chloride, Na, and then Cl? How it had little different spheres on it. They were different colors, remember? So this one's the similar, but with different types of things. This one has two gray hydrogens and one big red oxygen. That's so weird, Mrs. Cook. I thought we breathe oxygen, but if I breathe in water, I drown. Well, when it combines with hydrogen, you get something different. You get water. All right, so the shape, you see how it looks just like that Mickey Mouse? That's why my dad always called it the Mickey Mouse molecule. Now, this is just one water molecule. What does it look like when it actually becomes water? Well, they start to cluster up, right? The little Mickey Mouse ears have what's called a positive charge. For fourth grade, think of that as when you scoot your feet across the thick carpet in the cold of winter and you shock your sibling and they feel that little zzz, right? There's a little bit of electricity going on here. And that makes these molecules really sticky. It makes them want to stick and cling together when they pair up end over end like a whole cluster of magnets is another easy way of thinking of it. So see how they really want to be close together. And then when we add in other elements, so this one is salt, remember that NaCl from Tuesday, salt, then water is so special because it's really good at being a strong magnet that pulls apart other components, other materials like salt. So we'll get more into that today and then more into that next week for sure. But for now, I just want to show you, remember we talked about the three different states of water in a solid, liquid, or gas. This is what we think about when, like you want to draw a picture of it. But this is what scientists think about when they think about water in its three states. So see, it's that same little Mickey Mouse molecule. But when I have warm water, they have some space between them. Cold water, they're closer together. And ice, they are far apart. Now, usually when you have a solid, things get even closer together. These Mickey Mouse molecules, I would expect them to get even closer together. But water is a unique material in that its solid form actually has the molecules be wider spaced apart than when it's in a liquid state. And it's a unique property of water. This is why ice floats in water. Interesting. All right, here to tell us more about the wonderful properties of water is a scientist called Hank Green. Here we go.
Hello there. Here at Crash Course HQ, we like to start out each day with a nice, healthy dose of water in all its three forms. It is the only substance on all of our planet Earth that occurs naturally in solid, liquid, and gas forms. And to celebrate this magical bond between two hydrogen atoms and one oxygen atom, here today we are going to be celebrating the wonderful life-sustaining properties of water. we're going to do it slightly more clothed. Much better. When we left off here at the biology crash course, we were talking about life, and the rather important fact that all life as we know it is dependent upon there being water around. Scientists and astronomers are always looking out into the universe, trying to figure out whether there is life elsewhere, because, you know, that is kind of the most important question that we have right now. They're always getting really excited when they find water someplace, particularly liquid water. And this is one reason why I and so many other people geeked out so hard last December when Mars' 7-year-old rover Opportunity found a 20-inch long vein of gypsum that was almost certainly deposited by, like, long-term liquid water on the surface of Mars. And this was probably billions of years ago, and so it's going to be hard to tell whether or not the water that was there resulted in some life. But maybe we can figure that out, and that would be really exciting. But why? Why do we think that water is necessary for life? Why does water on other planets get us so freaking excited? So let's start out by investigating some of the amazing properties of water. In order to do that, we're going to have to start out with this. The world's most popular molecule, or at least the world's most memorized molecule. We all know about it. Good old H2O. 2 hydrogens, 1 oxygen. The hydrogens each sharing an electron with oxygen in what we call a covalent bond. So as you can see, I've drawn my water molecule in a particular way.
Don't worry about covalent bonds. That's advanced stuff. But just 4th grade know that it's got 2 hydrogens and an oxygen.
And this is actually the way that it appears. It is V-shaped. Because this big ol' oxygen atom is a little bit more greedy for electrons, it has a slight negative charge, whereas this area here with the hydrogen atoms has a slight positive charge.
For now, think of that as the 2 different ends of a magnetic pole. So like sometimes magnets push apart and sometimes they cling together. That's like positive and negative, different ends of them.
Thanks to this polarity, all water molecules are attracted to one another. So much so that they actually stick together, and these are called hydrogen bonds, and we talked about them last time. But essentially what happens is that the positive pole around those hydrogen atoms bonds to the negative pole around the oxygen atoms of a different water molecule. And so it's a weak bond. But look! They're bonding! Seriously, I cannot overstate the importance of this hydrogen bond. So when your teacher asks you, what's important about water? Start out with the hydrogen bonds, and you should put it in all caps and maybe some sparkles around it. One of the cool properties that results from these hydrogen bonds is a high cohesion for water, which results in high surface tension. Cohesion is the attraction between two like things, like attraction between one molecule of water and another molecule of water. Water has the highest cohesion of any non-metallic liquid, and you can see this if you put some water on some wax paper or some Teflon, or something where the water beads up, like some leaves of plants do it really well. It's quite cool. Since water adheres weakly to the wax paper or to the plant, but strongly to itself, the water molecules are holding those droplets together in a configuration that creates the least amount of surface area. It's this high surface tension that allows some bugs, and even I think one lizard, and also one Jesus, to be able to walk on water. The cohesive force of water does have its limits, of course. There are other substances that water quite likes to stick to. Take glass, for example. This is called adhesion, and the water is spreading out here instead of beating up because the adhesive forces between the water and the glass are stronger than the cohesive forces of the individual water molecules in the bead of water. Adhesion is...
There's a lot of vocabulary going on right now. Don't worry, just let it wash over you. Just enjoy. It's nothing you have to learn right now in 4th grade.
Attraction between 2 different substances, so in this case the water molecules and the glass molecules. These properties lead to one of my favorite things about water, the fact that it can defy gravity. That really cool thing that just happened is called capillary action. And explaining it can be easily done with what we now know about cohesion and adhesion. Thanks to adhesion, the water molecules are attracted to the molecules in the straw. But as the water molecules adhere to the straw, other molecules are drawn in by cohesion, following those fellow water molecules. Thank you, cohesion. The surface tension created here causes the water to climb up the straw. And it will continue to climb until eventually gravity pulling down on the weight of the water in the straw overpowers the surface tension. The fact that water is a polar molecule also makes it really good at dissolving things, which we call it's a good solvent then. Scratch that. Water isn't a good solvent. It's an amazing solvent. There are more substances that can be dissolved in water than in any other liquid on Earth. And yes, that includes the strongest acid that we have ever created. These substances that dissolve in water, sugar or salt, being ones that we're familiar with, are called hydrophilic. And they are hydrophilic.
Hydra, Latin roots, guys. Water. Phil means loving, something that loves water.
Like because they are polar, and their polarity is stronger than the cohesive forces of the water. So when you get one of these polar substances in water, it's strong enough that it breaks all the little cohesive forces, all those little hydrogen bonds, and instead of hydrogen bonding to each other, the water will hydrogen bond around these polar substances.
So think of that like the water's magnet is so strong that it can pull apart things like sugar and salt.
Salt is ionic, and right now it's being separated into ions as the poles of our water molecules interact with it. But what happens when there is a molecule that cannot break the cohesive forces of water? It can't penetrate and come into it. Basically, what happens when that substance can't overcome the strong cohesive forces of water and can't get inside of the water? That's when we get what we call a hydrophobic substance, or something that is fearful of water. These molecules lack charged poles. They are non-polar and are not dissolving in water because, essentially, they're being pushed out of the water by water's cohesive forces.
So that one was oil.
Water, we may call it the universal solvent, but that does not mean that it dissolves everything.
All right. That was Mr. Hank Green. There was a lot of information in that. Let's take a quiet little break, and then we'll come back for part 2. For part 2, I want you to have out your salt and water packet. This is the top part of it, salt plus H2O. Oh, we just learned about that. H2O means water. And then we're going to be doing pages 4 and 5 together, but we'll do that in part 2, so you have a little bit of a break, get a snack, play with a sibling, and I'll see you in just a bit.